1, November 29th. I just watched Clarence's new video, 1 hour 27 minutes. I played double speed, but I watched every minute of it. Enjoyed it. A lot of backstory, a lot of how he grew up. And man, he was a specimen. Well, he still is a specimen. Probably one of the best specimens. One of the most inspiring person to me on my life choices as well. Him being vegan is a very important thing to me. All right, and I did not progress on any of the C++, so we have to still do Java today. All right, let's see what we have today. Oh, by the way, I am using Doc Reader now. So that's why it's kind of screwed up. Wait, it's not screwed up anymore. Wait, is it not working here? Oh, it is. Huh. When you refresh, oh, I see. I think it starts to detect that it has dark mode, so it doesn't use it anymore. But anyway, I'm using Dark Reader now, and I contributed. I didn't pay for this much. I paid $5 a month. I think it's worth it. So now all my website is going to be dark. Actually, I'm not sure. Oh yeah, Google was dark already. Which website was not dark mode initially? Well, no, because before, when I click open the problem, it is not dark mode. But now, it is dark mode. Perfect. Alright, are you kidding me? Three hard problems in a row. Jesus, man. Valid arrangement of pairs. You're given... I was just thinking, the LeetCode team was like, okay, it's gonna be a Halloween weekend. Thanksgiving weekend. Let's just hit as many hard problems as possible. I think I haven't seen an easy problem for a while. It's either just a string of medium problem, I would say maybe like a week or maybe even more, and then they will hit you like 3 or 4 hard problems in a row. It has been this for a while. Can we see like a history of problems? Like what problem was the level? Actually, I don't know. I don't know where I can see. I mean, I can see my history. Where is my history? My lists? Submissions. Yeah, so this is the issue, right? The dark mode issue. You cannot see some stuff. Alright, yeah, so... Oh, it's the whole system. That's actually not. They didn't tell you the level of the problems. Okay. Yeah, that's alright. Let's just go do it. Doesn't matter. Hard, medium, easy. We're gonna do it no matter what. If we can't do it, we'll copy and paste and I'll learn it later. Alright, we have a zero indexed 2D integer array, pairs, where pairs I is start to end. An arrangement of pair S is valid if for every index I we have and I minus 1 is equal to start. Return any valid arrangement of pairs. The inputs will be generated such that there exists a valid arrangement. Hold on, I didn't understand. Let me do that one more time. An arrangement, so we need to arrange the pairs such that every previous AND is the new start. Very interesting. Actually, I think this is an interesting problem. Alright, so 5 1 4 5 11 9 and 9 4, right? Okay, 5 1. Do we have any start with 1? No, so 5 1 has to be at the end. And do we... Okay, how big is it? 10 to the 5th. So we can scan once to get the last. We scan another time, we can get a front because we say, do we have any front? That is 19, that is 11. Oh, but it says one way, so maybe There are multiple. Hmm. Yeah, there could be multiple that can end. No, it cannot be. No, no, no. It can be. It didn't say the two are. Oh, okay. So the start is not equal to the end, and no two pairs are exactly the same. And we need to just link them together, right? We need to link them together. Link them together. Would you have like a... We have a 4, 5, right? Would you have something else as a 5? Oh, it's possible. Because I can have a 5, 4. Then we can think, I see. Okay. Okay. So, yeah, that's not... That doesn't guarantee that it's... Well, if it only occurs once, then it's guaranteed to be the end. But if it doesn't occur once, then it's not. So that's not a scalable solution. Maybe we can see who and whom can be connected. It can be a graph problem, right? I think it's a graph. Basically, we say, okay, we have 5, 1, 5 and 1, right? And we have 4, 5. 4, 5 we can connect. It's a DAG. It's not like it's a directed graph. And 11, 9. I don't know where 11, 9 goes. And then we have a 9, 4. So here 9, 4. And 4 can connect to this. Right? So we can do this connection. Each one, yeah, is a node. And we can build a graph out of it. And the value is, Jesus, 10 to the 9th. Okay. So it has to use a map, right? And we'll connect them. Then we need to find the starting point. So eventually there will be like lots of things moving and going. But there has to be, actually it doesn't have to be a starting point. Anyway, so this one we have a starting point, right? Now second one is 1, 3. We connect it to 3, 2. And next is 2, 1. And 1, yep, exactly. So in this you can do anyone will valid, right? So basically we create the graph, and what do? We start from something, and we start to go to see if we can hit every. Then how do you know which one is the right starting point? I mean, it'll take ON to build the graph, and once the graph is built, let me try the last one. 1, 2, 1, 3, and 2, 1. So, you see 1, 2, 2, 1, and we can do this, right? And we have one of them that works. The other one does not work. We have a back edge. We can do in degrees, but in degrees, if you have 0 in degree, that must be the start, right? But in this case, this one has 1 in degree, this one has a 1 in degree, and this one has a 1 in degree, right? So you cannot just use in degree to decide which one should be the starting point. And if we just say, okay, we start from here, and then we go boom and boom, and then, yep, it's not gonna work, right? And then this one go back, so this is not gonna work. Then you have to start from another one. Yeah, that's the problem. That is the problem. So we build up the graph is easy, but how do we detect who to start from? I can start from Okay, how about this? We start from anyone. Okay, we start from anyone, and then we'll be able to progress to get a path. And man, this one might get another path, right? So we get some path, okay, and then we'll get a bunch of paths. Okay, we get a bunch of paths. So starting from something, I will get a path. Start from something, I'll get a path. Right? And because it says that there must exist a valid arrangement of pairs, which means if you start from any node, one of the paths must be correct. So you start from something and you go. Yeah, you go like however you want to go, and you get all the paths that originate from here. And you go to the next node, right? If the next node has already been visited in the previous round, that means it is one of the children in the original path. Oh, that does not negate it. It can still be the path that connects. Yeah, that is the issue. That is the issue. Because when you start from one and you go to the end, yeah, let's say like you have 5 or 4 different paths to go to the end, and each one you can create an array, right? And you can also say, okay, where are you, right? Which one you're at. And next one, if the next one does not exist in any of the path that has already been done, then you need to do a path from there, right? You need to do a path from there. Yeah, basically it's a question of graph. You have a graph, find the one path that can go through every single node. It doesn't feel that hard, but enjoy. Awesome. I mean, again, I don't think this will be that hard. Let's analyze, right? So eventually we're gonna have a chain. So maybe what we can do is still do the in degree and out degree analysis, right? If we still do in degree and out degree, because eventually, but you see this one is also one in degree and one out degree. So one in degree, one out degree doesn't necessarily mean that you will be, so maybe I need to go, when I go through the thing, I need to note that if a node, so yeah, basically a node, right? I can have its parent, I know its parent, and I know its children, right? You'll have an in degree and have an out degree. And does not matter if it has only one in degree and a one out degree. And if these two are not the same, then it must be in a straight line. Like we know that this is good, right? We can start from here and we can find another one that ends at here. So we can go through, look for nodes like this. Any node like this, that's okay, right? Any node like this. So yeah, so we can do a parent, right? So if I have one parent and a one child and then these two, because it's not possible that have everybody's like this, because this is just pointing this way. Actually, is it possible to have things like this? I don't think so. 1, 2, we'll go with 2, 1, and 1, 2. Dude, it's actually possible. So 1, 2, 2, 1, 1, 2, 2. Oh my goodness. My god. But hold on. We can still focus on nodes with one-on-one. Because it's either this, right? Or it's gonna be like this. There's only two possibilities for a node to have one in and a one out. So if it's this way, it must be along the way. So you can use this as a starting point to get somewhere, right? Using this, but this one can also diverge. But I guess if it also diverge, I don't know. Graph like this is always hard. Eulerian circuit. What the hell is Eulerian circuit? Okay, let's see. Yeah, it's a graph. Yeah. Wait, hold a second. Compare each pairs as edge. Oh, I didn't think about that way. Hold a second. So 1, 3 can connect to 3, 2. So that's a 1 to 2. Ah, I didn't think about that way. I just say 1, 3 go to 3, 2. And 2 and 2, so this one will go back to 1. Oh, this does simplify it a little bit. Right, 1, 2. So basically this is a 1 go to 1. So this is have a self edge. But how? I mean, I think this is actually make it even worse because you have to reconstitute at the end. Okay, it doesn't matter. It's the problem. We know the problem, and then we just need to have whatever the heck this is. All right. Yeah, this basically, I think if you don't know it, probably cannot solve it. What's Eulerian path? Oh, dude, I was looking at it before. Okay, in graph theory, an Eulerian path is a trail in a finite graph that visits every edge exactly once, allowing for revisiting vertices. Visiting every edge at least exactly once. Oh, visiting every edge. My God. Hold a second. 5, 1. This edge is 5, 1. And 4, 5. Right? This edge is 4, 5. 11, 9, and 9, 4. This edge is 9, 4. And 9, 11. This is 11. This is 11, 9. So Eulerian is saying a graph that you visit every edge exactly once, but you can revisit the nodes. Eulerian circuit or circle is an Eulerian trail that starts and ends on the same vertex. Well, we don't need them to end on the same circuit, so it doesn't have to be a circle. Oh, this is the one. Helmholtz's algorithm. Ah, I see. I think we have this type of problem. You can revisit node, but you have to connect all the edges exactly once. That's, you basically turn into here. But you still have the data structure issue, like how am I supposed to represent this? Right, you just visit all of them once Yeah, you can revisit. So I need to say, oh, I just do this, right? 11, 9, 9, 4. I have the edge 4, 4 to 5 and 5 to 1. It's a directed graph. All right, let's see if we can understand and without seeing the implementation. 1873. Choose any starting vertex and follow a trail of edges from that vertex until returning to V. It is not possible to get stuck at any vertex other than V because the even degrees of all vertices ensures that when the trail enters another vertex W, there must be an unused edge leaving W. The tour formed in this way is a closed tour, but may not cover all the vertices and edges of the initial graph. Oh, this is finding Euler cycles. We're not finding Euler cycles. As long as there exists a vertex U that belongs to the current tour, but that has adjacent edges not part of the tour, start another trail from U following unused edges until returning to U, and join the tour formed in this way to the previous tour. How do you mean by joining? Since we assume the original graph is connected. Repeat the previous step, but exhaust all edges of the graph by using a data structure such as doubly linked lists. What the hell? To maintain the set of unused edges incident to each vertex, to maintain the list of vertices on the current tour that have unused edges, and to maintain the tour itself, the individual operations of the algorithm, finding unused edges existing each vertex, finding a new starting vertex of a tour, and connecting the two tours that share a vertex may be performed in constant time. Alright, this is basically useless. I think we have to go with all paths and circuits along the edges of the graph are executed exactly once. And this already would delve deeper into understanding. It's a path in a graph that visits every edge exactly once. Have I done this before? Is that why I have seen this one already? No, I have not done this before. To find a path in a graph, the graph must satisfy certain conditions. So every vertex has an even degree. Oh, but that's a circuit. The graph has exactly two vertices with an odd degree. Oh, that's how you find where to start. Okay, let me redraw. So this is the first example, right? Second example, I have 1 to 3, 3 to 2, and 2 back to 1. Yeah, how I did not see that, right? Oh, then we can start from anyone because this is an Euler graph. So we can start from anyone. Okay, third example, 1 to 2, 1 to 3, and 2 to 1, right? So this one, it says the graph has exactly two vertices that has odd degree. Oh, this is not odd degrees. 1 to 2, 1 to 3, and 2 to 1. Oh, this is odd degree. 1, 2, 3. 1 is 3, 3 is 3. So one of them must be the starting point. Check connectivity. All right, we know that this definitely do. So we'll count out degrees. So count degrees of each vertex. Identify vertex with odd degree. So I'll do that. So if it's If we don't have odd degrees, then boom, we can just do whatever and then make it work, right? Determine the starting vertex. A path exists starting from one of the odd degree vertices. So I can choose any one, but if you don't have an out degree, then it is not going to work. Yeah, so we check for children, right? If this one doesn't have, then we can choose the other one. Okay, so it doesn't, I mean, for this one, it's the same. It's the same. You have odd numbers, right? What if both has odd numbers, like more than 3? I would choose any one. Okay, we'll choose any one. Okay, we choose a starting point. We traverse the graph to find. Okay, we'll traverse so use a stat to keep track of the current path and backtrack when necessary. Oh, so basically you already know, right? You already know the starting point just based on the odd degrees. You already know the starting point. That is true, right? You already know the starting point. Like here, I know the starting point is 1, so I'll go to 2, right? I'll go back to 1, which is fine because the edge is different. As long as we're not visiting the same edge, that is okay. And then 1 will go to 3. Traverse to find order. Yeah. I mean, let's say use a stat, basically just recursion, right? We use DFS to do this. Yes. Okay, so it's actually not that complicated. I think the most important insight is if the count of edge is even for all of them, so you just start from anyone, it will work. If it's odd, then you have to find a starting point. All right, so now the question is, when we build it up, okay, when we build it up, how do we do this? Yeah, we have a starting point, so we go to the next one, so we pass it in, right? And then from next one, I'll have, a bunch of children. I just choose one, right? I choose one, and then I'll put it in, right? And then we just keep going, and then boom, if it fails. What do you mean by if it fails? Well, we know the endpoint, right? So we need to get to the endpoint. If we get to the endpoint and it's not right, then we backtrack. Right now we backtrack. So eventually the correct answer will come. Okay. I think we can do this. Does this count as just reading the hints? I doubt it because we definitely know the solution. Right? It doesn't. I don't think it counts. I'm not gonna count it as just. I'm gonna count it as fail, but it's a different type of fail because we just don't know. All right, 2097. I count this as fail. Okay, this is a fail. However, although I was not able to solve it by myself, it did require some knowledge, in particular Euler's path. Right? I did realize that the problem is a graph, but there are 2 key pieces, right, that I was not able to intuit. Okay. First, treat each number in the pair as a node, right? Treat each pair as a node, and then thus the pair itself becomes a directed edge. The rule of Euler, right? The rule of Euler's path is to traverse a connected graph by visiting each edge exactly once with the while allowing, right? While allowing visiting the same nodes multiple times. 2. For a connected graph to have an Euler path, I have to have 2, right? Exactly 2, I think. Exactly 2. Yeah. There must be exactly 2 nodes with odd degrees, or all the nodes with even degrees. If 2 nodes have odd degrees, one of them must be the starting point, right? The starting point. If all the nodes have even degrees, then we have an Euler circuit, which means any node can serve as the starting point, right? Then the problem becomes a backtracking path finding, right? It's weird. Become a DFS with backtracking to find a path, right? And that uses all the edges. All right. Okay, so what you're supposed to do with this? We need to create a graph. Okay, so it's gonna be a map of integer. It's gonna be a list of integer graph new hash map, and then we're just gonna go through and we're gonna count, right? We're gonna count. We do this, we already have count. That is not true. We need to count the number of degrees. Okay, we need to count the number of degrees, so we need another map of integer, right? Degree counts, right? Degrees, new hash map. Okay, and then for int is actually edge, right, of pairs. We say graph dot put if absent edge 0. This will be new array list. Okay, and graph dot not graph degrees put if absent edge 0. So I'm going to put a 0 here, and then graph dot get edge 0 dot add edge 1. Graph dot get edge 0, right? Not graph. This is going to be degrees. No. Put. Oh my goodness, this is very bad. What do we do here? Put edge 0 degrees dot get or default edge 0 0 plus 1. We're gonna copy this for the other one as well. So this one's gonna be edge 1. This is gonna be edge 1. Yeah, because it's degrees, in degree and out degrees, right? So once we're done with all that, so we're gonna go through to find the 2, right? We can say int node 1, okay, int node 2. We can actually do -1. Node 2 equals -1, okay. Then we say for int key of degrees dot key set, right? We say if degrees dot get key mod 2 equal to 1, say if node 1 is smaller than 0, node 1 equal to k, else if node 2 is smaller than 0, node 2 equal to k, else nobody is, then both are done, then we can just break it. Okay. So now what we're gonna do, if node 1 is smaller than 0, because they have 2, right? When you say node 2 is smaller than 0, then then we can just any, right? Any we have an Euler. It's actually not Euler, Eulerian. I think that's what they call it. Eulerian. My bad. Eulerian. Oh, so Euler. Eulerian. Okay. So we have an Eulerian circuit, which means we can start from any node. Alright, so now we have to have a DFS, right? So the DFS I need a map for sure. Graph. I need a starting point, the current node, and I need, do I need a target? I do need a target, right? I do need a target. Oh, target. Number of edges. We passed this. When we hit number of edges, we're good, right? And we hit number of edges. But we can go back and forth. How do you know an edge has been visited before? How do you know? It's a good question. How do you know an edge has been visited before? Well, if a node that has been visited will get removed, then we know, right? Then we know. We'll pop it. And if it's backtracking, we just put it back, right? We just put it back, which means we don't need number of edges. Do we need number of edges? Hold on, let me think. In this case, 1, 2, 3, right? When we've done that, 3 gets popped, so 1 cannot go, right? 3 to 2, and then 2 will go to 1, and then that's it. Because 1 doesn't have any more edges, because I'm popping it. Every time I do, I pop it. Interesting. But what if the path is not right? So like here, right? I say this has to be the start. I go to 2, I remove this. 2 go to 1, I remove this. 1 will go to 3. Perfect. But if I go 1 to 3, right? And then 3 has nowhere to go. And then the length doesn't sound right. Then we have to go back, right? Then we have to go back, and yeah, you have to figure out how to do this, because I go back, basically backtrack. So I try the next one, right? I try the next one, and then I guess it's fine. No, I guess it's fine. No, I just need a number of edges. That's true. I think number of edges is good enough. So I have the node, I have a number of edges to check when it's good. And we also need a list of, I believe that's going to be an int, right? This is a path. Okay. So I start from the current node. And first thing, check if path.size is equal to num edges, return. Done. Okay, we're done. If path.size is not equal to, right, path.size is not equal to, then I need to say, ooh, I think I need to use a Boolean value, because this is need to return true, right? If it's not equal to, then I will check for int child of graph.get node. Or default. I have done something like this before. It should be empty list, right? So with this, what I'm gonna do? So I have a child, right? I need to go to a child, and I say from this child, I can put the current thing into the path, right? I can put the current thing into the path, and we say path dot add, okay, new int current node and the child, right? We put this in, and we call DFS graph child is the next node, num edges and a path, right? Oh, hold a second. If this is true, which means we have finished, then we will return true. If it's false, then path.remove path.size -1. We remove it, we try the next one, right? We try the next one. And we'll go through all this. If nothing works, we'll return false. Okay, so that's that. And then here, we can start from any node as the root. So we can say, hold a second. We need to have a list of int res new array list, right? So here we can call it DFS graph node. Did they say node always start from 0? Nope, there's no mentioning. Dude, then what am I gonna do? Oh well, it doesn't matter. We can do pairs. Well, we can do pairs. Jesus. We can do pairs here, because any node, right? So Paris, that's Paris. Pairs 0, 0. Yeah, because it doesn't matter. Anyone can be, right? This is going to be pairs.length. Path is just going to be res. Okay, so that's if we have a circuit. Else we don't have, so we must have 2, because it's guaranteed that it's work. So I have node 1 and node 2. Now we can say if graph.get node 1 dot size is equal to 0. So sum1 is the true ending, right? If that's the case, then We'll do DFS graph node 2 pairs.length and res. Okay. Else, then we just do node 1 pairs.length res. And at the end, we'll return res. Type mismatch. Oh, you gotta be kidding me. Alright. 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 You asked for it. You asked for it. So we need to do this. Dear me. Then why am I putting a path at like that? I could just go through the whole thing, right? I can just record a list of integer. That's all right. Let's just do it this way. It's okay. It's okay. It's okay. Pairs 2 and 4. That's actually not right. My bad. I equal to 0. I smaller than pairs dot length I plus. We say res I equal to path dot get I. It's actually not that bad. All right, now we return this. Oh, okay. Let's see. Let's see. It's 51. It has been. I have been doing this 1 hour every day. The goal has always been only do half an hour every day. Wait, what? That is correct. Get or default. Collections dot empty list. The goal is to always do half an hour, but when you get stuff like this, it's really hard to do half an hour. Yo, 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 what the hell? Oh, I went back. Oh, shoot. Oh, shoot. Oh, shoot. Okay. So we cannot just do it that way. All right, it's fine. It's fine. It's fine. Let me think. So basically, yeah. So we start from here. We go back. But we have to go back. Oh, right. We have to go back, but we need to also know that when we do this again, it has been visited already from node 1 perspective, right? Because node 1 I hit 2, and I'll go back to 1. There's gotta be a way. There's gotta be a way for me to represent which edge I have used. All right, we just need to figure out how we can do that. There got to be a way. So I need to know the edge, right? Whether an edge has been used. How do I do that? An edge has been used. An edge has been used. Yeah, I have to do that. An edge has been used. Hold on, I need to copy this because I made some changes. I need to check an edge has been used. What was the best way to check that? Think about it. You go 1 to 2, okay. So once you go 1 to 2, I can just delete it. Right? I can delete it. Yeah, I can delete 2. So when I get back to 1, the 2 does not exist. So basically what I'm saying is here. Don't do it like this. All right, we copy it first. Because it's a list, how do I copy a list? If I can, I don't want to copy, but copy array list. Or, you know, turn array list into, yeah, we turn array list, here. So it's an int children, okay? New int, I don't know, is there a way? I think there is a way, but how do I do this? List integer. Okay, list integer children. Okay, so we do this. Okay, so this is the children, and then we can have a copy. All right, children copy. I'm not sure if this is the best way to do it, but this is the way I think I can do now for int c of I equal to 0, I smaller than children dot size, I plus plus children copy I equals children dot get I. Okay, then for int child, let's call it c of children copy. Okay, we get from copy, so I can manipulate it, right? If it has to be a deck, because I need to pop it. Is I pop front and I go everything. Oh my god. Now we can pop from let's pop from the back. Pop from the back. Okay, so or pop from the back. If we pop from the back, do we even need to care about this? Hold on, if I pop from the back, I pop it and I go, it fail, right? Then what? Then I put it back in? Yeah, you pop it and you try it and it fail. Then what? Then you put it back in, then you pop the next one, right? It's really, you know, it's really hard to you need to turn this into it has to be a set, right? It has to be a set. So you can add it back and you can remove it. Man, there gotta be an easier way. Come on, think. I have a path, right? I have a path. How do I know which path it is? I can use maybe another mapping, right? From here to here, I record whether it has been used or not. But that's like a map of a map. Dude, I don't know. A map of a map? A map of a set. A set. So we start from something and then we end. So we make it into a set. So every time when we use an edge, we will remove it. And yeah, so we go 1 to 2, right? And once we do 1 to 2, we remove 2 from that map, right? From that map, and then we go 2 to 1, and then from 1, we check the map. Isn't that just the graph? Which means I just need to turn the graph into a set, and then it shall work, right? Hold on. I think this is what you're trying to do. So instead of we do a set, right? We can do a hash set. Everybody else is the same. And we can do this as empty set. Okay, and now we go back up. We change the graph into a hash set. Yeah, we do have to put it in this, because every time we use it, it has to be removed. So it's a set of this. This is going to be empty set. Okay. It's not hash set. It's just a set. Int I equal to 0 for int c of children plus equal to c. Okay, so now we go through every child, every c. If children dot contains c, right? If it does not contain, then there's no point. That means you shouldn't do it. Right. If children contain C, we will add C here, and children remove C, and it's going to be C. It will be true. Otherwise, we will reduce this and children dot add. We add a C back. And because this I just get the, so I'll get the address of it. So, okay. So we make this change. Let's see if it works. That was good. All right, let's try. I think I did not find a path for this. Oh. Oh my god. I got an error in the 4th. Dude, this is bad. Alright, let's see. We have 8, 5, 8, 7, 0 to 8, 0 to 5. Jesus. 8, 7, 0, 8 to 5, 0 to 5, 7 to 0, 5 to 0, 5 to 0, 0 to 7, 8 to and 7 to 8. Everybody's 2 except for 5. 1, 2, 3, 4, 5, and 8. So I start from I think I should go both. I think I should go both. Yeah, I think it's fine. So I'll do both. I kind of, yeah, I realized. So I'll do this. And then we say if path.size is equal to path.size if it's not equal to pairs dot size dot length, right? That's when we do it again. We'll path dot clear. I'm just guessing the API here. Then we do it one more time, right? We do that. Just guessing. There we go. So you do have to like run both times. Because I think what happens is just you go from one of them, because 5 and 8 both are good. So you go one of them, it doesn't work, so you have to go the other one. All right, let's try it again. So hold on, what's the runtime? We can handle the runtime. How difficult is the runtime? Let's do the runtime. So runtime, if we say on, right? On is gonna be for this part, and then this is okay. Let's do E and edge. So we have the edges, right? And we have a V nodes. And how about the traversal? Well, the traversal will go through every edge exactly once. So it'll be like this. Okay. Hopefully this one will be right, because it's already past 1 hour. I still have training to do. Come on. Come on. Oh, no, no. Well, we time out. Damn it. Damn it. Oh my god. Okay. That's not even a big test case, man. It's not even a big test case. Okay, it's decent sized, but I might have go through some, I don't know. I mean, I'm already removing the children, right? I'm removing it. I am removing it. How is that still timeout? All right, we have to do some debugging here. How do I do the debugging? Well, you do the debugging by, you know, I'll comment out some code. Okay, well, we still have to return some stuff. So I'll copy and paste this. And then I'll do this, I'll do this. I don't need to do this. System out the print line. I want to see node 1. I want to see node 2. Just make sure that it works. Right, node 1, node 2. Yep, I have 2 nodes, node 1 and node 2. And I start from node 1. And okay, let's say we start from 72, 73. Node 1, node 2. We just do right, node 2. Do we still time out? Then our traversal has some issues. Yeah, I do think our traversal has issues. Otherwise, it will not. It will be right. So one of the node, when I start from a node 1, it failed. It failed because of, I don't know, some forever loops. Am I just going some loops? But why would it be? Because this is not a copy. This is from here, right? Why would it cause this issue? Yeah, I go through every single children one time. Right? If I come back here, if it does not exist, then I'll go for the next one. I'll go for the next one. How do I prevent this? I mean, I can't even see how the problem originates. Yeah, it's this traversal. My God, how do I do this traversal? Then you backtrack. Then you try another one. Yeah, the point is I already done this. Unless... I don't know, man. I don't know, do you think it makes any difference? I really don't think so. I really don't think so. So what I'm trying to say is okay, let's do this. If graph dot contains key node, right? If graph does not contain this, return false. Otherwise, we don't use children. We just say, you know, graph dot get node. Again, I don't think that's the reason, but just to make sure that okay, and then that's the no one. Yep, still not right. So the original weight is fine. I need a bit more. I need a little more. Let's say graph dot get. Just kind of take a peek. I should do the other one. So this one has 2, this one has 1. I have some suspicion. Let's also get degrees. So 1 degree is 1. Yeah, it's definitely the start. This degree is 5. Okay, we can do we're going to say if degrees dot get node 1 equal to 1 and graph dot get node 1 dot size equal to 1, then DFS, then we definitely use this. Right, and now we can say else if 2, right, then we do 2. Else if one of them does not have, right, graph dot get node 1 dot size is equal to 0, which will actually just, oh man, hold on. Degrees dot, not degrees, graph dot contains key node 1. If it doesn't contain node 1, then we do node 2. If it doesn't contain node 1, or it contains so if it doesn't contain node 1, or it do this, then we do this, right? Else if graph dot contains key node 2, if it doesn't contain node 2, or degrees dot get node 1 is this and this and this, then we do node 1. Else, so both has multiple, I don't know, we have to try both. I feel like this is still not right. I still think there may be a, I don't know, edge case where this will not work. Alright, I still feel like there could be edge cases that's not gonna work. I can try it again. Yeah, this will work, and use example test case including this one we got wrong. Let's try it here. I think everyone has to be dot get or default. empty set, right? Yeah. Okay. Try one more time. All right, let's try it. Yeah, I think we still hit this thing. Yeah, it's the issue with the traversal. Damn it. How? Like this one, oh my god. I'm gonna lose it. Like if I do this first, I think we'll pass. If you just do the other one, it's there we go, yeah. How? How do I do this? How? I have no clue. Like one of them just will go into, I don't know, go into a cycle? If you go into a cycle, you should stop. You should stop. If you get into a circle, you cycle, you stop. Dang it. All right, this is a traversal issue. We'll have to do it tomorrow. I mean, we basically solved the majority of it, but it's traversal. I mean, this is really embarrassing. We got stuck on the traversal. How do we do the traversal? I don't want to check the solution for this. I need to figure out how to do the traversal. I mean, it is different because it's not revisiting the same. It's revisiting the same edge, right? But I thought I already handled it if you revisit the same edge. I mean, we can have edge visited, right? That's basically another way to do it. If you have visited the edge, then you just don't do it. But I get the current children out, right? This is based on the current children. What the hell? All right, one last debugging Okay, one last debugging. I wanted to see. Okay, I wanted to see what the hell is happening here. So how do I see? I will print out the path. How do you print out the path? Or maybe you can print out the node. Oof. I don't know, maybe we can do for P of path. Can you say system.out.print arrays.toString P, and then system.out.print I don't know. I don't know what's gonna happen. I hope we can get some printout. Yep, it'll be helpful. Yeah, so we start from this. Okay, maybe it'll be more helpful if we can do, I don't know, actually it's too small. Let's open a new one. All right, what do you see? I mean, is there any repeats? Yeah, you're not gonna find any repeats just by doing this way. My guess is there is no repeat, but you're just going back and forth, back and forth, back and forth, and that is, really giving you issues. Right? You go back and forth, back and forth, back and forth. But that's the thing. Like I already exited. Right? I don't understand. I already said that if the current children contains, I'll try it. But if it does not, then I will return. Then I go for the previous one and try the second child. And this one can go bunch of stuff and then fail, and then unwind and try it again. Oh. Okay, there's another thing that I can try. I said this is the last one, but maybe there's something with the nodes, Again, system.out. We have string.format. We have node 1. Count degrees and children. All right, this is the last effort. If this one doesn't work, I need to stop and think about it. I think it's collections. No? List? Come on, I just want to print. Oh, it's a set. Dude, I cannot print? You gotta be kidding me. Print? How do I print a set? That is stupid. Oh, you can print directly? Really? I am not sure. I'm honestly not sure. We can print directly? Oh, maybe we can. Oh wow, we can. Okay. Degree 3, children 1. Degree 3, children is 2. Yeah. I don't know. It's definitely not this. We cannot analyze from this. We just need a better algorithm to traverse. Gosh. How do I traverse? All right, let's just call it for today. We have this one. Yeah, I'll think about it. It's late. All right, I'll see you guys tomorrow. Adios.